Right now, the most powerful quantum computers in the world have one massive problem. They need to be colder than outer space to work. We're talking negative 459 degrees Fahrenheit. That's just a fraction of a degree above absolute zero, the coldest temperature physically possible. This means quantum computers require building-sized refrigeration systems, cost millions of dollars, and are completely impractical for everyday use. But researchers at Stanford University just changed everything. They built a quantum device that works at room temperature, and it could eventually put quantum computing power in your pocket. To understand why this breakthrough matters, you need to understand why quantum computers are so ridiculously cold in the first place. Quantum computers use qubits instead of classical bits. While a regular bit can only be a 0 or a 1, a qubit can exist in multiple states simultaneously, a phenomenon called superposition. Even more powerful is entanglement, where qubits become mysteriously linked. Measure one, and you instantly know the state of its partner, no matter how far apart they are. But here's the catch. Qubits are incredibly fragile. The slightest disturbance, a single photon of light, a vibration, even the thermal energy from room temperature air can destroy their quantum state. This is called decoherence, and it's the enemy of quantum computing. To prevent decoherence, companies like Google, IBM, and others use dilution refrigerators that cool their quantum chips to about 15 millikelvin, that's 0.015 degrees above absolute zero. This works, but it means quantum computers are massive, expensive, and completely impractical for most applications. You're not going to carry a dilution refrigerator in your pocket. Until now, the idea of a room temperature quantum device was considered almost impossible. In December 2025, a team led by Professor Jennifer Dionne and postdoctoral researcher Dr. Feng published a paper in Nature Communications that could change the future of quantum technology. They created a nanoscale device, smaller than a human hair, that can entangle photons and electrons at room temperature. The device uses a material called molybdenum diselenide, a two-dimensional material just a single molecule thick, placed on top of a specially patterned silicon surface. Here's where it gets fascinating. The silicon surface is designed with tiny notched squares that create what the researchers call twisted light. When light hits this surface, it doesn't just bounce off, it starts spinning in a corkscrew pattern, technically known as orbital angular momentum. These spinning photons then interact with the molybdenum diselenide layer, transferring their spin to electrons in the material. This creates entanglement between the photon's spin and the electron's spin. Dr. Feng explained, "This platform allows us to more efficiently entangle the spin of photons with the spin of electrons, all at room temperature." Previous attempts at room temperature quantum devices achieved what's called a degree of polarization of less than 0.10. The Stanford team achieved 0.5, a five-fold improvement, and a new world record. Let's break down the science a bit more. The key concept here is something called valley polarization. In certain 2D materials, like molybdenum diselenide, electrons can exist in different valleys. Think of them as different energy states. The Stanford team designed what's called a chiral metasurface, a surface with a specific handedness, like your left and right hands. This surface selectively interacts with light based on its spin direction. When left-handed circularly polarized light hits the surface, it enhances emission from one valley. Right-handed light enhances the other. This selectivity is what enables the quantum entanglement. The team also leveraged something called the Purcell effect. By designing the metasurface to resonate at specific wavelengths, they enhanced the rate at which quantum transitions occur by a factor of 13. The result? A device that maintains quantum coherence at room temperature without any cryogenic cooling. So what can we actually do with room temperature quantum devices? Unhackable communication. Quantum key distribution uses the laws of physics to create encryption that's mathematically impossible to break. Any attempt to intercept the message destroys it. Room temperature devices could make this practical for everyday use. Ultra-precise sensors. Quantum sensors can detect incredibly small changes in magnetic fields, gravity, or temperature. This could enable earlier disease detection, better brain imaging, and more accurate navigation systems. Artificial intelligence. Quantum computers excel at optimization problems and pattern recognition. Room temperature quantum chips could accelerate AI training and enable new types of machine learning algorithms. Dr. Pan himself mentioned the possibility of quantum phones. Maybe someday we could do quantum computing in a cell phone, but that's a 10-plus-year plan. The team estimates quantum networks could be viable within 5 years. Miniaturized devices for everyday use? That's a decade or more away. This Stanford breakthrough isn't happening in isolation. In late 2024, Google announced their Willow chip, which demonstrated quantum error correction at scale. IBM continues to push the boundaries of superconducting qubits. China has achieved quantum communication over satellite links. But all of these systems still require extreme cooling. The Stanford approach represents a fundamentally different path, one that could eventually make quantum technology as ubiquitous as smartphones. According to McKinsey, the quantum computing market could be worth $28 to $72 billion by 2035. Quantum communication could add another $11 to $15 billion. The race to practical quantum technology is accelerating, and room temperature operation might be the key to winning it. We're still years away from quantum phones or desktop quantum computers. The Stanford device is a proof of concept, not a finished product. But what this breakthrough proves is that room temperature quantum operation isn't just theoretically possible, it's practically achievable. The future of quantum computing might not be in massive frozen facilities. It might be in devices small enough to fit in your hand, operating at the same temperature as the room you're sitting in right now. If you want to stay updated on the latest breakthroughs in quantum computing, AI, and emerging technology, make sure to subscribe and hit the notification bell. And let me know in the comments, what would you do with a quantum computer in your pocket?